The symmetric group Sn plays a central role in the theory as well as the applications of group representations. In this lecture, we are going to recall some of the basic properties of Sn, which will be useful in studying the theory of representations of Sn. We are going to go into the details of representation theory for the symmetric group in later lectures. As you will all recall, Sn is nothing other than the symmetric group of permutation of n objects. So a typical element in Sn is a bijection from a set of n objects to itself. That's exactly what a permutation is. Just as an example, let me take an element pi from S4. It's a mapping which maps 1, 2, 3, 4 bijectively onto the same set 1, 2, 3, 4. And one possible example, which I have written down here, is pi maps 1 to 2, 2 to 3, 3 to 1, and 4 to 4. You can see this permutation illustrated graphically here. 1 goes to 2. That's what the permutation does to 1. It also takes 2 to 3. So that's what this arrow tells you. It takes 3 back to 1. So you end up with a cycle with 1, 2 and 3 going into each other. And 4 of course goes into itself. One standard way of denoting this permutation happens to be by means of this matrix-like object. All that this says is it takes 1 to 2, pi 1 is 2, 2 to 3, 3 to 1 and 4 to 4. Of course, this statement here, this diagram here and this notation all say exactly the same thing. One more notation which we use for permutations is very, very important, and you will soon see why it's important. It's the so-called cycle notation. In fact, that has been graphically seen here. As I said, 1 goes to 2, 2 goes to 3 and 3 goes back to 1. So that's a cycle. So what you do is you put 1, 2, 3 in a square bracket, call that one single cycle. And 4 of course goes to 4. That's in a cycle on its own. Very often when we write down a permutation, we omit one cycle. So we could have written down the same permutation just as a cycle 1, 2, 3. Note that when you say 1, 2, 3, it means 1 goes to 2, 2 goes to 3 and 3 goes back to 1. So this particular example of ours has one single one cycle, that's this one here, and a 3 cycle, a cycle of length 3. I'm pretty sure that all of you have realized by now that the labels 1, 2, 3, 4 are really not that important. Instead of 1, 2, 3, 4, we could have used alpha, beta, gamma, delta, or maybe cats, dogs, sheep, and men. But it is a convention that we usually use the first n integers 1 through n as targets for permutations. That makes the notation a lot more consistent. Now, when we are talking about the cycle notation, we have to be careful about one thing. The cycle 1, 2, 3 takes 1 to 2, 2 to 3, 3 to 1. But it can also be written down as 2, 3, 1 because that will also take 2 to 3, 3 to 1 and 1 to 2. Similarly, 3, 1, 2 is exactly the same cycle as the cycle 1, 2, 3. So, the cycle notation for a given permutation, although it's very, very useful, it's not unique. That is something we have to be very careful about in what comes in the future. So, our permutation, which is 1, 2, 3 and a 4 on its own, could also have been written down as 2, 3, 1 and a 4 on its own, or 3, 1, 2 and a 4 on its own. They are exactly the same as 1, 2, 3, 4. You take a look at another example. Let's talk of a permutation which is a permutation of 7 objects and member of S7. So, I've taken a very simple example here. 1, 2, 3. They form a 3 cycles. So 1 goes to 2, 2 goes to 3, 3 goes back to 1. 4, 5 forms a 2 cycle, 6, 7 forms another 2 cycle. Now, I could have written this down just as well as 2, 3, 1 because 2, 3, 1 does exactly the same thing as 1, 2, 3 does. And they kept 4, 5 intact. That's just my choice. I could have also written down 6, 7 as 7, 6 because that's exactly the same thing as 6, 7. 6 goes to 7, 7 goes to 6. The same thing happens here. Or there could be other ways of writing this down. For example, I could have written the 1, 2, 3 as 2, 3, 1, same cycle. I could have written down the 6, 7, 2 cycle first, and then I could have written down the 4, 5, 2 cycle. That would of course give you exactly the same effect. So there are multiple ways of writing down the same permutation using the cycle structure. And that is going to be very important in what is going to come. Now, as we have said over and over again, permutations form a group. Of course, if you have a group, one thing you must have is a set, and the next thing you must have is a binary operation on the set, a way to quote-unquote multiply elements of the set to yield new elements. Now, in the case of permutations, the so-called multiplication rule is rather obvious. After all, permutations are maps. They are bijective maps from the set 1, 2, 3 up to n to itself. And the standard way of multiplying, or well, in this group sense multiplying maps, is just composition. You do one map after another. So to illustrate that, let's take a look at two distinct elements of S4. Pi is the same permutation that we have seen before. 1, 2, 3, 4 goes to 2, 3, 1, 4. And sigma is another permutation which takes 1, 2, 3, 4 to 2, 1, 4, 3. So sigma multiplied by pi, the group multiplication here would simply be composition. That is, sigma star pi acting on 1 will give you sigma acting on pi 1. Pi gets to act first and then sigma gets to act on the result. Now what is pi 1? Pi 1, of course, as this says, is 2. So sigma of pi 1 is just sigma of 2. And sigma of 2, of course, here is 1. So sigma star pi acting on 1 is 1. On the other hand, is sigma acting on pi 2. Pi 2, of course, is 3. So we are looking at sigma 3, and sigma 3, of course, is 4. And you can easily write down the other two results following the same pattern. So the resulting permutation sigma star pi is 1, 2, 3 and 4 goes to respectively 1, 4, 2 and 3. That has been written down in this particular matrix-like notation that we have used before. Now, in fact, this notation actually makes it very easy to calculate the product of two permutations using a very simple trick. That is what I am going to explain now. Note that sigma takes 1 to 2, 2 to 1, 3 to 4, 4 to 3. What is important in defining the sigma is which elements go where. Of course, you don't really have to write this in the order 1 goes to 2. You could have just as well said 2 goes to 1 first. So, an alternative way of writing down sigma would be, I take 2, 3, 1, 4 and say where they map. So 2 of course maps to 1 here. The same thing happens here. 3 maps to 4. So here also 3 is mapping to 4. 1 maps to 2 in sigma. That's exactly what this says. And 4 maps to 3. That's exactly what this says again. So it's obvious that this is exactly the same permutation as this one. It's just another way of writing down sigma. Now, the reason why I have chosen to write down the top row of sigma in this particular manner is simple. It is exactly the bottom row or the result of pi. So, if you talk about sigma and pi being composed, sigma star pi, notice 1, 2, 3, 4 gets taken to 2, 3, 1, 4 by pi. That's this line in the middle. And 2, 3, 1, 4 gets taken to 1, 4, 2, 3 by sigma. So basically, after you readjust the order of the top row in sigma, 1, 2, 3, 4 is changed to 2, 3, 1, 4 and write sigma accordingly, then writing down sigma star pi is trivial. All you have to do is take 1, 2, 3, 4, the top row of pi, and 1, 4, 2, 3, the bottom row of this ordered way of writing sigma, and that's it. So you can just forget about this intermediate step and you get 1, 2, 3, 4 maps onto 1, 4, 2, 3. Just to illustrate this again by pi star sigma, here sigma gets to act first, so 1, 2, 3, 4, 2, 1, 4, 3 is fine. What I need to do is rewrite pi. So this is of course the lower line of sigma. what I need to do is rewrite pi so that 2143 is what sits in the front. So 21 would mean 32 down here. 43 of course would swap these two. 1, 1, 4 would become 4, 1. And then composition is straightforward. 1, 2, 3, 4 goes to 2143 and 2143 goes to 3241. So the composition is simply 1, 2, 3, 4 goes to 3241. Now an important point that you must have noticed here is the sigma star pi and pi star sigma take 1, 2, 3 and 4 to distinctly different elements. In other words, the group product here is not an abelian product. The fact that this group product satisfies the other demands of a group is pretty easy to verify. I will leave that as an exercise for you. But the upshot of all this is, under this composition rule, Sn becomes a non-abelian group. I say in general non-abelian because the smallest Sns, S1 and S2, are actually abelian. That's pretty easy to see. But the general Sn is a non-abelian group. As you can see in this example, S4 is obviously non-abelian because sigma star pi and pi star sigma, these two products differ from each other. What we are interested in, of course, is the theory of representations of Sn. And as you may recall from our previous study of representation theory, conjugacy classes play a very important role in the theory of representations. Now, in general, figuring out the conjugacy classes of a given group can be quite laborious. Remember, two elements are in the same conjugacy class or are said to be conjugate to each other if there is an element in the group which conjugates one into the other. In other words, G1 and G2 will be in the same conjugacy class if there is an element G3 such that G3, G2, G3 inverse is G1. Now, if two elements are not in the same conjugacy class, figuring that out would in general require you to go through the entire group, conjugate with every element and try to see whether you can get the second element from the first one or not. And only if this fails completely, can you really say that the two elements are not in the same conjugacy class. So in general, figuring out conjugacy classes of a large group, and Sn, remember, has n factorial elements, so for even a moderately big n, Sn is a pretty large group, this would be a rather non-trivial, time-consuming task. However, for Sn there is a very important result which makes it rather easy to figure out the conjugacy classes. And the statement of that is simply this. The conjugacy classes of Sn are determined by the cycle structure. Two permutations are in the same conjugacy class if and only if they have the same cycle structure. This immensely important statement certainly requires a proof. And the proof of this hinges on this very simple observation that if sigma and pi are two permutations in Sn, then sigma pi sigma inverse acts on sigma tau, where tau is one of these objects, 1, 2, 3 up to n on which the permutations act, to give, well, sigma pi sigma inverse acting on sigma tau is simply through composition. So sigma acts on tau first to give you sigma tau, then sigma inverse acts on that, then pi acts on that, then sigma acts on that. Of course, this sigma inverse completely reverses action of this sigma, and so this is the same as sigma acting on pi tau. So pi takes an element tau to pi tau. Sigma tau is taken to sigma of pi tau by sigma pi sigma inverse. So if pi is, for example, this particular permutation, something which has 1 3 cycle, 1 2 cycle and 1 4 cycle, 1 2 4 3 5 7 9 and 6 8 being the cycles involved, then sigma pi sigma inverse will simply take sigma 1 to sigma 2, right? Because pi takes 1 to 2, sigma pi sigma inverse takes sigma 1 to sigma 2, pi takes 2 to 4, sigma pi sigma inverse takes sigma 2 to sigma 4, and pi takes 4 back to 1. So sigma pi sigma inverse takes sigma 4 back to sigma 1, just using this obvious result. Similarly, this 3579, which was the cycle in pi, gives rise to a similar cycle in sigma pi sigma inverse, which consists of sigma 3, sigma 5, sigma 7, sigma 9. The 682 cycle in pi becomes sigma 6, sigma 8 in sigma pi sigma inverse. So it's obvious that in this case at least, you started with a permutation with a 1-3 cycle, 1-2 cycle and 1-4 cycle. The resulting permutation after you conjugate is also one which has 1-3 cycle, 1-4 cycle and 1-2 cycle. Now while we illustrated this with a particular example, it should be pretty easy to generalize this to any situation. If pi has a certain cycle structure, sigma pi sigma inverse will have exactly the same cycle structure, with just the elements within the cycle labels being changed by the application of sigma. Now, conversely, if you think of another permutation, given pi which has this particular cycle structure, let's think of pi prime, which is a different permutation with the same cycle structure, 1-4 cycle, 1-3 cycle, 1-2 cycle. So now, what we can always do is find a sigma which will actually conjugate pi to pi prime. So that is, pi prime will be sigma pi sigma inverse. All you have to do is to ensure that the cycle structure is preserved here. So 3579, the 4 cycle, actually has become the 1432 cycle. So if your sigma maps 3 to 1, 5 to 4, 7 to 3 and 9 to 2. So 3 to 1, 5 to 4, 7 to 3 and 9 to 2. And then goes on to map 1 to 4, the elements of this 3 cycle onto 5, 8, 9 respectively. 1 to 5, 2 to 8 and 4 to 9. And maps 6, 8 to 6, 7. So 6 goes to 6, 8 goes to 7. This particular permutation sigma will of course produce this pi prime from this pi if you calculate sigma pi sigma inverse. So here we have seen that if two different permutations have the same cycle structure, you can always find a sigma which will map one into the other through conjugation. Once again, I have given a specific example here, but all of this can be easily generalized. And this should be enough to convince you that two permutations will be in the same conjugacy class if and only if they have identical cycle structure. Same number of 1 cycles, same number of 2 cycles, same number of 3 cycles and so on. In other words, a given conjugacy class of Sn can be uniquely labeled by non-negative integers nu1, nu2, nu3 up to nu(n), which are nothing but the number of 1 cycles, 2 cycles, 3 cycles, n cycles respectively, which are present in this particular permutation. Of course, since you have only n objects which are being permuted, you must have a constraint here. This particular conjugacy class, which is denoted by 1 to the nu1, 2 to the nu2, 3 to the nu3, all the way up to n to the nu(n), and of course if some of the nu's are 0, then you may not write them at all, must obey this particular constraint. If you have nu1 1 cycles, the total number of elements in those 1 cycles is of course 1 times nu1. The nu2 2 cycles have a total of 2 nu2 elements in them. The nu3 3 cycles, a total of 3 nu3, and of course the n nu(n) cycles has n times nu(n). So total number of elements which are being permuted has to be the same as n. So this constraint has to be obeyed. 1 times nu1 plus 2 times nu2 plus 3 times nu3 plus all the way up to n times nu(n) is the same as n. This of course puts trivial constraints on the possible values of nu1, nu2, nu3 and so on. For example, it's obvious to see the only possible value for nu(n) is 1 or 0. In fact, for any L bigger than n by 2, the only possible value for nu(L) is 1 or 0. That's easy to see. And in general, you can figure out all possible combinations of nu(i)s for a given n rather simply, and that will be able to label all the different conjugacy classes which this particular permutation group Sn will have. For example, in the case n equals 5, that is, for S5, the possible cycle structures are, of course, 1 to the 5, we could have 5 1 cycles. Then, of course, is an element which essentially has 1, 2, 3, 4 and 5 each in their own 1 cycle. And that means, of course, that we are talking about the identity element here. You could also have a situation where you have 1 2 cycle, but the moment you have that, you cannot have 5 or 4 1 cycles. In fact, you can only have 3 1 cycles. So 1 cube 2 is a possibility. Then you could have 2 2 cycles with a single 1. By the way, if you have a situation like this, you could write 1 to the 1 2 square, or very often we don't write the 1 to the 1, as we have not written 2 to the 1 here, for example, and we write 1 comma 2 square. The comma is simply to ensure that you don't confuse it with a 12. Then, of course, you could have this 1 3 cycle and 2 1 cycles. You can't have 2 3 cycles here, of course. You could have 1 1 cycle and a 4 cycle, and you could finally have a 5 cycle. Now, these are the possible kind of cycle structures you can have. And this tells you that S5 actually has 6 distinct conjugacy classes. And from our theory of representations, it means that S5 has 6 irreducible representations. So the character table for this would be a 6 by 6 table. Now, because of this particular constraint, 1 times nu1 plus 2 times nu2 plus 3 times nu3 up to n times nu(n) is n, the connection between nu1, nu2, nu3 on one hand and the number n on the other is slightly non-trivial. Now, it should be easy to understand that as n increases, figuring out these cycle structures and hence possible classes of Sn gets more and more difficult, and that's essentially because you have a somewhat non-trivial relationship between these integers nu1, nu2, nu3, nu(n) and n, namely this one. There happens to be a rather simple one-to-one correspondence which makes our job a lot easier. This is between the partitions of the integer n and the conjugacy classes of Sn. This is what we are going to explore now, and we are going to explore this starting from this basic equation. Now, what we do here is define n integers lambda 1 through lambda n by the following relations. Lambda 1 is the sum of all the nus, all the cycle sizes. Lambda 2 is the sum of all of them except for nu1. Lambda 3 is the sum of all of them starting from nu3, so nu1, nu2 are dropped. And going on down the line, lambda n minus 1 is simply nu n minus 1 plus nu n, and lambda n is the same as nu n. Now you can see one very obvious thing here. If you were to add all of these together, you are definitely going to get the left hand side here. So sum of the lambdas, sum of these n lambdas is exactly equal to n. Not only that, it's also easy to see that lambda 1 has to be bigger than or equal to lambda 2, since nu1 cannot be negative. Of course, nu1 can be 0. There may be no 1 cycles in the particular permutation you're looking at. Then, of course, lambda 1 will be equal to lambda 2, but lambda 1 can never be less than lambda 2. Lambda 2, on the other hand, can never be less than lambda 3, and so on. So you have this sequence of non-increasing numbers. I shouldn't say strictly decreasing numbers, because lambda 1, lambda 2 may be equal, but they are strictly non-increasing numbers which add up to n. Now the ways in which you can split up a given integer n into non-negative integers is called a partition, and this non-increasing demand actually ensures that we don't count partitions twice. Remember, 4 plus 1 plus 1 is 6, but 1 plus 4 plus 1 is also 6. We don't count these as two distinct partitions, we count them as the same partition, and in order to ensure that, we use this non-increasing sequence result, we are going to write the partition as 4, 1, 1, not as 1, 4, 1. And that is automatically ensured here by the definition of lambda 1, lambda 2 up to lambda n. So each cycle structure, nu 1, nu 2 up to nu n, will give us a partition of the integer n. On the other hand, given lambda 1 to lambda n, we can also uniquely determine nu 1 through nu n. Simply put, nu 1 is simply the difference between lambda 1 and lambda 2. Nu 2 is difference between lambda 2 and lambda 3. And this continues all the way down to nu n minus 1 being lambda n minus 1 minus lambda n. The only somewhat outlier is nu n, which is the same as lambda n, although you can make it conform to the same formula simply by defining lambda n plus 1 to be 0. So, you can uniquely determine the lambdas from the nus and the nus from the lambdas. And the lambdas, of course, provide a partition of the integer n. Since the nus tell you exactly what the cycle structure of a given permutation is, and hence can be used to label a conjugacy class of Sn, here we see that every partition of the integer n given by lambda 1 through lambda n will uniquely determine these nus and hence will uniquely determine a conjugacy class. So there are as many conjugacy classes of Sn as there are partitions of the integer n. To illustrate this basic idea, let us go back to our old example of S5. The partitions of 5, which are non-decreasing sequence of integers which add up to 5, are the following. You can have 5 alone. You can also, of course, have 4, 1. Then you can have 3, 2, 3, 1, 1, 2, 2, 1, 2, 1, 1, 1, and 1, 1, 1, 1, 1. So a total of 1, 2, 3, 4, 5, 6, 7 partitions. So 7 distinct conjugacy classes. So let's illustrate how each of these partitions give rise to a unique cycle structure. For 5, we have lambda 1 equal to 5 and lambda 2, lambda 3 which are not written, of course 0. So nu 1 is 5 and nu 2, nu 3 etc. are all 0. So this is a situation where you have 5 1 cycles, that is the identity alone as the only element in that particular conjugacy class. Now the partition 4, 1 means nu 1 is 4 minus 1, that's 3, and nu 2 is 1 minus 0, that's 1. So you have 1 cube, 2. 3 1 cycles, 1 2 cycle. 3, 2, this particular partition corresponds to 3 minus 2, that is 1 for nu 1, and 2 minus 0, that is 2 for nu 2. That's 1, 2 square, or 1 to the 1, 2 to the 2. 3, 1, 1. 3 minus 1 is 2, that's nu 1. 1 minus 1 is 0, that is nu 2 is 0. 1 minus 0 is 1, nu 3 is 1. So 1 square, 2 to the 0 we don't write, so we have 1 square 3. Then we have 2, 2, 1, which gives you 0 for nu 1. 2 minus 1 equals 1 for nu 2 and 1 minus 0, 1 for nu 3. So 2 to the 1, 3 to the 1, or 2, 3 without the 1. That comma would simply be a way of not confusing this with 23. That's all. 2, 1, 1, 1, the other partition. Nu 1 of 1, nu 2 of 0, nu 3 of 0, nu 4 of 1. So 1, 4. So 1, 1 cycle, 1, 4 cycle. And this, of course, gives you 0 values for nu 1, nu 2, nu 3, nu 4, and gives you 1 for nu 5. So that's a single 5 cycle, denoted by 5 to the 1 or 5. So we have recovered all the possible cycle structures for S5 using the partitions, and this has given us the 7 possible conjugacy classes. If you have been paying attention, you must have noticed a mistake that I have made a while ago. Here we can see that S5 has 7 conjugacy classes. A while ago, I had counted the conjugacy classes by listing out the cycle structures and had said that S5 has 6. That, of course, was a mistake. And that should actually teach me not to try to improvise things in the middle of a lecture. But anyway, if you go back here and look carefully, you will see that here I had missed one particular cycle structure, which is simply this structure, 2, 3. 1, 2 cycle, 1, 3 cycle. That was not listed among this. That of course brings the count of conjugacy classes and hence the number of irreducible representations up to 7 and a 7 by 7 character table, not a 6 by 6 one as I mentioned a while back. Now this should also illustrate the advantage of dealing with partitions which are actually easier to handle because you have a much simpler demand. You just want integers which add up to n rather than integers which are equal to n after weighting by 1, 2, 3, 4 and so on. So it's actually less error prone to go via partitions than via this directly. I would have been very happy to be able to claim that I made this mistake deliberately in order to illustrate how powerful partitions are as a method of keeping track of classes and hence irreps of Sn. But frankly, I just made a mistake in counting when I listed out all possible cycle structures. But the point is, partitions are easier to handle than cycle structures directly. And this actually illustrates the strength of this method of using partitions to label all the conjugacy classes. That said, it is actually common practice, especially in the physics literature, to label the conjugacy classes of Sn using cycle structure rather than using partitions. Now, I'm not very sure what the reason behind that is, but that is the common practice and that's what I'm going to follow. One important advantage which the cycle structure affords is the following. As you all are aware, the number of elements in a given conjugacy class of a group is a very important quantity, especially in the theory of representations. And if you ask the question, how many distinct permutations are there in a given conjugacy class of Sn? The answer to that is easy to arrive at in terms of the cycle structure corresponding to that conjugacy class. So, for the conjugacy class which has nu1 1 cycles, nu2 2 cycles, nu3 3 cycles and so on, the number of distinct permutations in that class is given by the following formula. N factorial divided by 1 to the power nu1 into nu1 factorial, 2 to the power nu2 into nu2 factorial, 3 to the nu3 into nu3 factorial, all the way up to n to the power nu_n times nu_n factorial. So this is a pretty neat formula for the number of elements in a given conjugacy class, and we can use it whenever we need that number. Now, why is this formula at all correct? In order to understand this, let me start from an example. We are going to consider a specific conjugacy class in S11 which has 2 1 cycles, 3 2 cycles and 1 3 cycle. So what we have done here is we have drawn this structure of 2 1 cycles, 3 2 cycles and 1 3 cycle in the abstract form here, where these solid circles just indicate certain elements from 1 to 11 which will go in there. So one example of course would be this one, where we have filled up these spots with the numbers 1, 2, 3, 4 right up to 11. Now, if I were to put these 11 numbers in a different order in here, I would still get 2 1 cycles, 3 2 cycles and 1 3 cycle, as long as these square brackets are not moved around. Now, of course, given that there are 11 numbers, the number of ways in which we can play around with this, number of ways we can permute these labels is actually 11 factorial. That's the n factorial that you have in the formula. However, every one of these 11 factorial permutations of the labels 1 through 11 does not really give rise to a new permutation. So if you have a permutation of the labels 1, 2, 3, 4, etc., which swaps, say, the 2 1 cycle. So a permutation which swaps the label 2 with the label 1, or the 3 2 cycles among each other. Say the label 3 4 gets swapped with 5 6. or 7, 8 gets swapped with 3, 4. All of these would lead to exactly the same permutation, just a different way of writing it. That's not all. 3, 4 is exactly the same as 4, 3. So even within a 2 cycle, there would be 2 distinct ways of writing a 2 cycle, which would lead. There would be 2 distinct ways of writing a 2 cycle, which would lead to exactly the same permutation in the end. 3, 4 is exactly the same as 4, 3. 9, 10, 11, the 3 cycle, can also be written as 10, 11, 9 and 11, 9, 10. In fact, irrespective of what particular labels land up in the 3 cycle, there would be 3 distinct ways of writing it, which would all lead to exactly the same permutation. So, all these 11 factorial permutations of the labels do not give rise to distinct permutations in the end. This actually overcounts the number of distinct permutations by this factor, 2 factorial, which would be the number of ways you can swap the 2 1 cycles around, times 3 factorial, which is the number of distinct ways you can swap the 3 2 cycles around. On top of that, you would also have extra factors of overcounting of 2 each for each of the 2 cycles, because each of the 2 cycles can be written down in 2 distinct ways, which would mean exactly the same thing. So that gives a factor of 2 cube. And the single 3 cycle contributes an extra 3 factor, because ABC, BCA and CAB would mean exactly the same thing. Thus, we have a total number of distinct permutations in this particular class as 11 factorial divided by the overcounts. The overcounts is 1 square into 2 factorial, 2 cube into 3 factorial, and 3 to the 1 into 1 factorial. Of course, I have written it in this form in order to make it conform with the formula that we had written before. Here, of course, the only things that matter are the 2 factorial, 2 cube, 3 factorial and 3 to the 1, which is exactly the overcount that we have. And after you cancel out all the common factors between the numerator and the denominator, what you end up with is the number of elements in this particular conjugacy class, which turns out to be 69,300 in this case. So, as you can well imagine, the conjugacy classes that we have to deal with in SN for even a moderately large n are pretty huge. And so, if we were trying to find out the character table, say, for Sn, then direct calculations of the kind that we had carried out earlier for smaller groups may not be the best technique to use. Indeed, there are specialized techniques available for Sn in particular, which renders the job of calculating the different irreps, their characters, the dimensions, much easier than is suggested by the sheer sizes involved. Another property of permutations, which is calculated rather easily from the cycle structure, is a parity of a given permutation. Let me remind you that every permutation can be achieved by a finite number of transpositions, specific permutations where you only switch 2 elements at a time. Now, it should be easy to understand that the number of transpositions that you need to carry out a particular permutation is not really unique. After all, the identity permutation, where nothing changes, can be achieved with no transpositions at all, or can be achieved by carrying out a switch between any 2 elements and then switching them back again. Transpositions being self-inverse, doing 2 transpositions, 2 identical transpositions, undoes their effect completely. So you can carry out the identity permutation with no transpositions, 2 transpositions, 4 transpositions, but not an odd number of transpositions. And this is an important result in general. That is, the number of transpositions required to achieve a particular permutation is not unique, as we have just seen, but the parity of this number is. Whether this number is even or odd is fixed for a given permutation. Now, a permutation is called even permutation if the number of transpositions required for it is an even number. If the number required is odd, then you call it an odd permutation. Now, the cycle structure actually makes figuring out the parity of a particular permutation very, very easy. If you focus on a single cycle, it's easy to see that an L cycle can be achieved using L-1 transpositions. For example, if you want to achieve the cycle 1, 2, 3, 4, which actually changes 1 to 2, 2 to 3, 3 to 4 and 4 back to 1, you can achieve that by switching 1 and 2. This is a particular specific permutation which only transposes the first two elements. So of course, 1, 2, 3, 4 after the switch becomes 2, 1, 3, 4. Not what you want, of course. But after that you can apply the switch between 2 and 3. This is what I am denoting by P23 here. That switches the second and the third element. So 1 and 3, which were the second and third element after P12, becomes 3 and 1 respectively. So if you apply P12, P23 in this order, that is P12 first and then P23, 1, 2, 3, 4 becomes 2, 3, 1, 4. You finally want to get to 2, 3, 4, 1. For that you have to switch these two labels. So you have to apply P34, the permutation which switches the third and the fourth label. After you apply P23, P12, and these three permutations taken one after the other, it's going to produce a cycle 1, 2, 3, 4 going over to 2, 3, 4, 1 respectively. It is easy to see that this holds in general. So we get a very important result. How do you tell whether a permutation is odd or even? By looking at its cycle structure. All you have to do is check how many even cycles it has. Odd cycles all have parity plus 1 or all have even parity. Even cycles have odd parity, but even then, if you have two even cycles, you will have basically an odd number of transpositions for each, leading to a total even number of transpositions. So a permutation can be an odd permutation only if it contains an odd number of even cycles. So just look at the cycle structure, find out how many of these cycles that go into this particular permutation is even, and if that number happens to be an odd number, then you have an odd permutation. Otherwise, your permutation is an even permutation. So, for example, the cycle 1 cube, 2 to the 3, 4 to the power 2 happens to have 3 even cycles of length 2 and 2 even cycles of length 4. The total number of even cycles happens to be odd, so this is an odd permutation. Whereas 2 cube, 4, 3 to the 5, this permutation has 3 even permutations of length 2, 1 even permutation of length 4, which makes the total number of even permutations equal to 4, an even number, so this is an even permutation. In all of this, we don't bother about the odd cycles at all, simply because they always correspond to even permutations. We have now acquired enough background information to begin a serious study of the character table of Sn and in general other aspects of its representation theory. We are going to start that from the next lecture. But just as an appetizer, let me remind you of the few cases of character tables for Sn which can be worked out without much effort. These are of course the smallest few Sns, S1, S2 and S3. And these are the ones we are going to talk about now. And of course the approach we are going to use here is just a direct approach. Well, for S1, that's pretty straightforward. You have only one element which is being permuted, so there's only one permutation. The element gets taken to itself. That's the identity permutation. A class whose cycle structure is just one, there is only one cycle there, and has only one element, and the corresponding character is trivially the number 1. The identity representation, remember, is something which every group must have. Here S1 has only one class, hence only one irreducible representation, which happens to be the identity representation. S2 on the other hand, permutation of two objects, actually has two elements. One of them is composed of two 1 cycles, that's the element 1, 2, which is nothing but the identity operation. And the other one is one which has a single 2 cycle, which is the cycle 1, 2. Of course, both of these conjugacy classes have exactly one element each, which is also easy to understand given the fact that S2 is a abelian group. In an abelian group, every conjugacy class has only one element each. Now, two classes, hence two irreducible representations, two sets of rows in the character table, of which chi1 is simply the identity where every one of the elements gets represented by 1. The other one is also an example of a one-dimensional representation which every Sn has, except that for S1 it happens to coincide with the identity representation. This is a so-called alternating representation where all even permutations end up being mapped to 1 and the odd permutations end up being mapped to -1. That this is a valid one-dimensional representation. And remember, for one-dimensional representations, the characters are the same as the matrix elements, the 1 by 1 matrix elements that make up that representation. Is pretty easy to check from elementary algebra. Let us now move on to the first non-abelian Sn that we will meet. In fact, all Sns for n greater than or equal to 3 are non-abelian. S3 just happens to be our smallest example of that. Now for S3, the order of the group, written small g or mod of g, is just 6. There are 6 permutations of 3 objects, and the possible partitions of this number 3 happens to be 3 itself, or 2 plus 1, or 1 plus 1 plus 1. So therefore there are 3 classes and hence 3 irreducible representations. We also know from the theory of irreducible representations that if you add up the squares of the dimensions of these representations, you must get the order of the group. So we are looking for 3 perfect squares, 3 non-zero perfect squares, which add up to 6. And it is easy to see that the only possibilities are 1, 1 and 2. For the dimensions, 1 square plus 1 square plus 2 square is 6. So we have 3 adapts. They are 1, 1 and 2 dimensional respectively. And with this information, we can build up the character table to a large extent already. You label the columns of the character table by the classes, the 3 classes which correspond to 1 cube, which is of course the partition 3, which gives you new 1 equals 3. Then the partition 2, 1 gives you new 1 equals 1 and new 2 equals 1. That is a cycle with 1 entry and a cycle with 2 entries, 1, 2. And finally you have 1 plus 1 plus 1, which has 0, 1 cycles, 0, 2 cycles and 1, 3 cycle. That's this one. And the number of elements in each one of them can be easily figured out just by enumerating the elements of S3, or you could just use the formula that we had worked out. After all, 3 factorial divided by 1 cube times 3 factorial is just 1. That's the number of elements here. 3 factorial divided by 1 into 2 for this particular class happens to be 3. And 3 factorial divided by 3 is 2, which is the size of this particular conjugacy class. Now what about the rows of the character table? The characters themselves. We already know one representation, which is the identity representation, in which each class gets represented by the number 1. So that's one representation that we always have. The other one-dimensional representation which all Sn have is the alternating representation, where you replace each even permutation or a class which has even permutations with the number 1 and a class which has odd permutations with the number -1. And that immediately gives us chi2 equals 1 minus 1 and 1. Note that the first class, 1 cube, corresponds to 3 1 cycles, all odd cycles, all even permutations. So you get an even permutation overall. The second class, 1, 2, has a single 2 cycle which requires an odd number of transpositions. So The second class gets the number -1. And the third class, which has a single 3 cycle, all the permutations in this class happen to be even permutations, and so you have just the number 1 associated with it. What can we say about the third row? Now, one thing we do know is that for the identity element which belongs to the first class here, the corresponding matrix representative has to be the identity matrix, and hence its character has to be the dimensionality of the representation. Because we know that the third irrep of S3 is 2-dimensional, we know that the entry in the first column for chi3 has to be 2. We do not know the other 2 entries as yet, so let me just call them alpha and beta. We will figure out what alpha and beta are without even working out a representation of S3, but just by looking at some basic properties. The orthogonality property for characters, which is a very important result in representation theory, goes as follows. If you take chi-i mu's conjugate, multiply it by chi-i nu, where mu and nu labels to different irreps, weight this thing by the number of elements in the ith class and sum up over all classes. The result is either 0 if mu and nu are different, or g if mu and nu are the same. Remember, here we only consider inequivalent irreducible representations. So if mu and nu are different, the two irreps are definitely inequivalent to each other. And this orthogonality relation is something we have derived starting from the great orthogonality relation which follows from Schur's lemma. Now, applying this orthogonality relation between chi1 and chi3 gives the following. Number of elements in a class 1, chi1's entry 1, chi3's entry 2. That's 1 times 1 times 2 in the sum on the left hand side of the orthogonality relation. Then you have number of elements 3 into 1 into alpha. That's the second entry here. Finally, you have 2 into 1 into beta, and this has to be equal to 0 because of course 1 and 3 are inequivalent irreps. That gives us one relationship between alpha and beta, namely 3 alpha plus 2 beta is -2. The other relationship that you need can be figured out very easily by looking at chi2 and chi3. So 1 into 1 into 2, 1 into 1 into 2, plus 3 into -1 into alpha, plus 2 into 1 into beta. That's -3 alpha plus 2 beta equals -2. And these two equations can be solved rather trivially to give you alpha equals 0 and beta equals -1. So you can just complete the table here just by replacing alpha by 0 and beta by -1. This gives us a complete character table for S3. Well, actually you could have got this result even more easily by using the completeness of characters, which says that if you multiplied chi mu I star with chi mu j and summed up over all irreps mu, you would get g by gi times delta ij. In other words, if you looked at the character table and multiplied the columns with each other, then you would get 0 if you are using different columns. 1 into 1 plus 1 into -1 plus 2 into alpha would have given you 0. That would have told you that alpha is 0. Similarly, 1 into 1 plus 1 into 1 plus 2 into beta would have given you 0. That would have told you beta equal to -1 directly. Either way, you have managed to figure out what these two elements are and completed the character table for S3. Now, S4 of course has more classes. In fact, it's easy to see that S4 actually has 5 classes. S5 has 7, as we had worked out a while ago. And the character tables become bigger and bigger. And the direct method does not really work that well. For example, for S4, you would need 5 rows in the character table, of which 2 can be filled up on the basis of elementary properties. One is the identity representation, the other the alternating one. But that still leaves us with 3 rows to fill, with only at best the dimensionality of them known from the sigma di square equal to mod g formula. Not an easy task at all. In fact, you will need to go in for extra information before you can fill up the whole table. And things get worse if you go to higher and higher ends. So we will need specialized methods. And those specialized methods are things that we are going to talk about in the next few lectures.